Okay, so we looked at redox last time, and we're going to take it to the next level, and we're going to look at these two things called oxidizing agents and reducing agents. And do you know what? It's not actually that much more complicated. It's just complicated because there's a lot of terms here. But if we go through it slowly, it should make sense. So first of all, I want to draw your attention to an oxidizing agent. And what that does is it's basically something that oxidizes something else. So if it oxidizes something else, then it has to be reduced at the same time. We're going to have a look at some examples of what these might be, but just have it in your head that if something is an oxidizing agent, an agent is something that does something. So you can imagine like an FBI agent is somebody that works for the FBI. Well, an oxidizing agent is something that oxidizes something. And if it oxidizes something, then it must be reduced itself. It also accepts electrons, so it would gain electrons. I'll put that in as well. So I think the thing here is try not to overthink it. Just think an oxidizing agent is reduced, or an oxidizing agent gains electrons. Just think that rather than what it does, if that makes sense. A reducing agent is something that's the opposite, okay? So that is something that accepts electrons or gains electrons. It is something, that's one that donates it, so it gives them away. So it must be oxidized itself, okay? So it loses electrons. Okay, so just try and remember these two. It does the opposite itself of what it says. So an oxidizing agent is reduced. A reducing agent is oxidized. What those agent things are talking about is what it does to the other thing. So hopefully that makes sense. So let's think about where these might be and what they might be. Basically, if you think about the left-hand side of the periodic table, those are all metals. And metals, we know from National 5, lose electrons. And that is because they have electron shells that maybe have only 1, 2 or 3 electrons in the outer shell. We know that the atom is more stable when it's got a full outer electron shell. So these electrons are quite happily lost. If you want to talk about it in higher terms, then you know that those 3 electrons in an outer shell are further away from the nucleus, so it's quite easy to allow them to be removed. It doesn't take much energy to remove them. So those ones on the left hand side, they're easily removed. They're oxidized themselves, which means these are good reducing agents. Okay, and then on the right hand side, we know from National 5 that non-metals tend to gain electrons, and that's because they have a high electronegativity. Obviously they want to gain electrons, they've been pulled in, all that stuff, and they tend to form ions by gaining electrons, so they are obviously good oxidizing agents. And we can see that there. So if you're thinking about what a reducing agent is, then you're thinking of something on the left hand side of the periodic table, something with a low electronegativity, something with only a few electrons in its outer shell, that are quite easily removed. If you're thinking about an oxidizing agent, then you're thinking of something with a high electronegativity. It's got quite a lot of electrons in its outer shell, and maybe it could only take a few more just to complete that. Okay, so that's what we're thinking about here. So group 1 are actually really good reducing agents, and also I should mention group 7 for the non-metals, they're really good oxidizing agents. One of the things you're going to learn about oxidizing agents is that they are quite good for bleaching things, and actually chlorine, bromine, iodine, they're all kind of bleaching and disinfectant. You actually find they kill bacteria, and that's one of the things that's used in hospitals. If you're ever going for an operation, they actually rub some iodine on your skin first before they cut it open, and that's because it's a disinfectant. and it cuts down on the chance of infection. So reducing agents on the left, best ones are group 1, and the oxidising agents are on the right, best ones are group 7. Okay. Again, this is just another wee thing to kind of cement this. Metals on the left hand side of the periodic table, they ionise so they become ions by electron loss, so they must be called reducing agents because they're oxidised themselves. And non-metals on the right hand side of the periodic table ionise by electron gain, so they're gaining electrons, so they're reducing, so they must be oxidising agents. And I think it's just thinking about this terminology, it might be quite handy to maybe draw that diagram in a note somewhere just so you can see it and visualise it, and like what we did here, maybe put reducing agents, oxidised, and these are reduced. Something that allows you to see all this happen at once and kind of make sense of it. I think that would probably be the best idea for this. But if you are kind of confused about any of this, I would actually go back and rewind and kind of just go from the start again, just to make sure it makes sense, because there's a lot of terms being thrown about here. But I think if you group them like this, it makes it quite easy to understand. And I think it's the complicatedness of the agent. And I think just remember that an agent does something, so a reducing agent reduces something else. So it must be itself oxidised, and I think it's just thinking about that. Okay, so I think it's important to note that we've also got these permanganate is a strong oxidising agent, and it's important to see that it's not just elements that we've looked at before that can be oxidising and reducing agents, molecules and ions can be as well. So if we look at this one here, potassium permanganate is actually a really, really powerful oxidising agent. And that is because it's been very highly reduced. You can see it starts on this side as Mn7+, and that's reduced to Mn2+, so that's gaining 5 electrons. And what actually happens in this particular reaction I'm going to show you, it can oxidise the glycerol very strongly to carbon dioxide and water, and it produces actually quite a fiery reaction. We've also got this reaction here, we've got manganate again, that ion here, and also dichromate, and they are acidified potassium dichromate, and you might have acidified potassium permanganate. We have used these in Unit 2 when we were working out if we were working with an aldehyde or a ketone, and what we've seen was that obviously if it was an aldehyde, then that could be further oxidised to the alkanoic acid, and if it was a ketone, it could not be oxidised at all because it had no more hydrogens. It had nowhere, it had no, you couldn't turn it in to a more oxidised form. So basically, when we did this, these were the colour changes we've seen. If we use potassium permanganate, it went from a purple colour to colourless if it had the aldehyde had been oxidised, and if we used potassium dichromate, then it went from an orange to kind of khaki green colour if it had been oxidised. Obviously there was no colour change if it was a ketone because it cannot be oxidised. And in these you can see that each of those are being reduced as well. Okay, this is gaining 5 electrons, this is gaining 6 electrons. So these are being reduced themselves. They're very powerful oxidising agents, especially in the presence of acid. We're going to look at the blue bottle experiment, and you're going to see this. Basically it's methylene blue, which is a kind of dye, and we can add in some sugar along with some potassium hydroxide, and you'll see that what happens is the methylene blue is reduced by the alkaline dextrose solution, so that's a sugar solution, and it produces a colourless solution. When you shake it back up, there's oxygen in the bottle or in the flask, and that produces the blue dye again, so it would be reduced again, it would be oxidised again. And then we need to take the stopper off for more oxygen to come in, so I'm going to let you see that just now. Also, we've got this hydrogen peroxide. That's a strong oxidising agent, and in fact it's used all over the place for bleaching products. All these oxidising agents are quite good at bleaching as well. We said that. You might have used it if you have ever dyed your hair to be blonde, and what that does is it basically oxidises the proteins and colours in your hair, and then you get that kind of bleach blonde look. And then also, if you've ever spilt it on your skin, you can get like a kind of white mark. That is because it's bleached the kind of top layer of your skin. And also we use it for a kind of medical use. Hydrogen peroxide can be used to kill bacteria. So I have heard of people having a kind of very low concentration like mouthwash, and that can oxidise and kill bacteria in their mouth. So it's quite good, but we're going to see how it can be used for something special, and that is the elephant's toothpaste. And what happens is you've got this hydrogen peroxide reacting to produce water and oxygen. However, there's an actual catalyst in here, and it's potassium iodide. What happens is some of the iodide ions are converted to I2 molecules by the hydrogen peroxide. So you can see this here. The hydrogen peroxide is being reduced. So it's a powerful oxidising agent, and that reduces the iodide. Oxidises the iodide. However, what happens is when that reacts, it produces some more. The iodine would dissolve back in the water to produce iodide, and then it's a kind of cyclical reaction, so that's why it's used as a catalyst, because you can get your product back at the end, so you end up with more iodide being produced, and that you'll get to see that just now. And because of the fact that that's happening at a very high rate, and the catalyst is constantly being produced, then because you might put a small bit of catalyst in, a small bit of potassium iodide, you get lots and lots of foam being produced. So it's important to note this for the fact that what strong oxidising agents are used for. And basically, as I've kind of mentioned and suggested throughout, they can kill fungi and bacteria, which can inactivate viruses. So that's why they're kind of used in disinfectants and kind of cleaning agents. So for example, bleach is made up of something called hypochlorite, which has chlorine in it, and what happens is it will do its reaction, it kind of produces a kind of chlorine bleach at some point, and that's why you can, when you use bleach, you can smell that kind of chlorine-y smell. Obviously it's used in pools, chlorine as well, to kill bacteria and stuff from people going in and out, and we've talked about iodine as well. The oxidation process is also an effective means of breaking down coloured compounds, making oxidising agents ideal for use as bleach for clothes or hair. Again, I've seen people bleach their clothes with actual household bleach, as well as like hydrogen peroxide bleaches as well. So they do change colour, and they can actually kind of break down colour molecules. So hopefully that makes sense. I think there was quite a lot of talking through this, so I think the main points to know are to be able to understand what a reducing agent is, what it does, what happens to it, same for oxidising agent, and also be able to understand that metals tend to be good reducing agents and non-metals tend to be good oxidising reagents, and also to be able to understand it's not just elements that can do these, it can also be molecules and group ions as well. And also this stuff here is quite important as well, being able to understand what strong oxidising agents are good for. Hopefully that makes sense. If you need a hand, then I think maybe get in touch with your teacher, or maybe go back and revisit the video just